Hello guys, today we are discussing a topic in probability. So I am not just going with the basics, I am just going a bit forward and we will start with Bayes theorem. So here Bayes theorem. So why this Bayes theorem is required in probability? Then what is the difference compared to other topics in probability and Bayes theorem? So students, to know this much detailedly, we shall take an example why actually Bayes theorem is required. So let us consider an experiment, students. So that experiment involves collecting some balls or drawing some balls from the bags which are present in front of us, and those bags consist of some white and red balls. Here I am repeating again, we need to consider the experiment of drawing the balls from the bags which are present in front of us. So let us consider, for time's sake, we shall consider two bags, students. Here these bags, that is bag 1 and bag 2. Here this bag 1 consists of 2 red and 3 white balls, and this bag 2 consists of 4 red and 2 white balls. So these are the two bags which we have got. So now, as I told you, this experiment is drawing the balls from the bags, right? It means I can draw the red ball. It means also that I can draw the white ball. For time's sake, once again students, let us consider that we are drawing the white ball. So now, let us consider some event, say A, which is nothing but drawing the white ball. So students, now drawing the white ball, right? So we can draw this white ball either from the bag 1 or from the bag 2. It means getting the white ball is dependent on what, students? It is dependent on the bag 1 and bag 2, right? So now it comes conditions there. What is that condition, student? That is nothing but if we draw a white ball from the bag 1, that is nothing but P of A bar. What is here? What it is dependent on? It is dependent on this event E1. What is this event E1? Selecting the bag, right? So which bag it is? Bag 1. Similarly, let us consider this. That is nothing but E2. What is this E2, students? This E2 is nothing but selecting the bag 2. Is that right? So now this white ball can be drawn from where, students? From the bag 1. That is why here this is dependent on bag 1. If this white ball, drawing the white ball is dependent on bag 1, then what we get, students? Here we get 3 by 5. And similarly, if I draw a white ball from the bag 2, that is P of A bar E2, then what we get here? We get 2 by 6. So this is the probability what you have learned in conditional probability. Is that right? Now my question is, what is the probability that you draw a ball from the bag 1? You draw a ball from the bag 1 if it is given that the ball drawn is white. Okay, I will just repeat once again, students. What is the probability of selecting the bag 1 if, what is the probability of selecting the bag 1 if you have already drawn a ball of white color? This is what is happening here. So if you see this question, you may feel that this is not the regular probability. Why not the regular probability? Why? Because here the bag is kept first. Is that right? So after the bag is kept first, all the balls are present in it, right? So what we do? We first go near the bag and then select the white ball. Is that right? This is what we do, right? But now what I am telling that already I am predetermined to select the white ball, right? So now I need to know what is the probability that I have selected bag 1, what is the probability that I have selected bag 2, right? So now I am predetermined to select the white ball, and now I need to know that what is the probability of selecting bag 1 if we are predetermined to select the white ball. So let us use the condition of the basic probability definition and try to get the answer for this, right? So what is that definition, students? We know that the probability of any event is nothing but total number of favorable cases divided by total number of possible cases, right? So now my question is, students, what we need to find here, right? So I'll just state here, we need to find probability of selecting bag 1 if it is given that white ball is drawn. So what does this actually mean? This is nothing but finding the probability of what? Selecting bag 1 means even, right? Bar. It is dependent on what? It is dependent on selecting the white ball. So what was actually taken? White ball. White ball was taken as selecting the ball white, or it's taken as what? A, right? So we need to find now P of even bar A. Now students, we shall use this definition. So what are the possible cases involved here? The possible cases. So what are the possible cases, students? Possible cases are nothing but you can select the bag 1. Is that right? This is the first possible thing. Second possible thing is we can select the bag 2. If you select bag 1, what is the probability here? P of even. Right? If you select bag 2, what is the probability here? It is P of E2. Right? Now, if you select bag 1, what is the next job you are doing there? You are selecting a white ball. Is that right? So it means after reaching this bag 1, you are selecting the white ball. Right? Again, if you move to bag 2, what are you doing there? After reaching the bag 2, you are selecting what? Once again the white ball. So here you do P of A bar E2. So combining this, we get the possible cases. Now we need to know what is the favorable case out of this. So what is the favorable case? So here, favorable case is nothing but selecting the bag 1. Is that right? Now I am reaching only the bag 1. So P of even, right? After reaching this bag 1, what we are doing here? We are selecting only the white ball, right? So here we get P of A bar even. So now using this definition, how can I write? So probability of this is what we are finding, that is even bar A, right? Which is equal to what? Favorable case, that is nothing but P of even into P of A bar even, all divided by P of even into P of A bar even plus P of E2 into P of A bar E2, right? So this is when we consider only the two events, E1 and E2, right? So there are some confusions here. What are those confusions? So why did I take only plus here? That is the first thing, right? So because by the additional theorem of probability, we know that intersection also come into play, and white has disappeared. There should be a reason here. That is the first thing here, right? So let us clarify one by one all those doubts by proving the base theorem. So in order to prove the base theorem, there are some prerequisites which should be known. So what are those prerequisites? That is nothing but the partition of a sample space. So now let us come across the partition of a sample space. So remember this, please note down this somewhere, and after proving the base theorem, we shall come into the similar conclusion. Okay? So now we shall come across the partition of the sample space. Okay, so what do you mean by partition? Have you heard about the word partition? Yes, you have heard. It is nothing but dividing. So we have got the sample space. That sample space should be divided into what? Some subsets which are called as events. Those can be elementary events. Those can be compound events. Let us talk about it in future. but now this sample space should be divided into events, right? So can you just simply keep on dividing it? No students, it is not at all possible. If you do that, then that is not called as the partition of a sample space. In order to partition the sample space, we need to follow certain procedures here. What are those procedures? First one, that is, if we consider, let E1, E2 and so on up to En be the n events of a sample space S. Okay, then these events are said to be the partition of a sample space S. Then the first condition it should prove is E1 union E2 union and so on up to En should belongs to or should be equal to S. So if the union of all these events equal to S, then such events are called as exhaustive events. Got it? So the first condition, all these events should prove is what? Considering the union of all those should be equal to what, students? It should be equal to S, right? See, when I took an example there, I told that we are considering two bags, right? So I considered E1 as what? Bag 1 and E2 as what? Bag 2. So combining together E1 union E2, what does it give? Total collection for us to select the balls, right? So E1 union E2 was a total collection of bags which we add in our experiments, right? Now coming to the second one. What is the second one here? EI intersection EJ should be equal to empty, right? So can it be every time true? No, there are certain conditions here for I not equal to j. It means I cannot consider E1 with E1 here because I and j will be equal to what? Same thing, 1, right? I couldn't do that. So what I need to do here? I need to consider this condition, that is I not equal to j. And what are the values I can give for I? I equals, or I and j, I comma j equals 1, 2, 3 and so on up to n. This is what I can do here. Okay, so this is the second condition, students. So similarly here, I call these events as exhaustive events, and then this can be called as pairwise mutually exclusive events. Yeah, students, you are already right. It is pairwise mutually exclusive events, and I think if you remember in sets, you have also called it as what? Disjoint sets. There is no much difference here, students. Just the name is different here. That's all. There we call disjoint events, and here we call what? Mutually exclusive events. That's all. There is nothing more than that. And the third one, which is very much important, that is nothing but P of EI should be greater than 0 for all I. So here you know that the probability of any event can be 0, but I am not considered here it as equal to 0. Why? If I tell P of E1 equal to 0, it means what? That event is an impossible event, right? So I cannot consider here any impossible events. So I need to consider certain events which has got some probabilities. Got it? So this should be always greater than 0. So these are the three prerequisites which are required to prove the Bayes theorem. Okay? So now let us use these prerequisites to prove the Bayes theorem. So let us start with Bayes theorem here. So Bayes theorem, as I told you, we need to use those prerequisites, right? So in the statement, we shall use those prerequisites and come to a conclusion of the equation what need to be proven. Okay? So here, statement. So first, we need certain events here, like E1, E2 and so on up to En be n partitions of a sample space S. of a sample space S of a random experiment. RE is nothing but random experiment. Okay. So here I am telling that these events are nothing but the end partitions of a sample spaces. Apart from this, we also need to consider one other event, that is nothing but event A, and let A be any event of a sample space S. So if you remember the examples what I considered before, that E1 and E2 was considered as what? Bags. And what was that event A, students? Nothing but the drawing the ball, right? It was part of the experiment. What was the experiment given? We need to draw the balls from where? From the bags, right? So your bags, here the drawing the ball, all are what? All are part of the experiment. Okay. So here considering the bag 1, considering the bag 2 are certain events, and similarly considering or drawing the white ball, drawing the red ball are what? Are also the events of the same experiment. Okay. So here E1, E2 and here forms what? The partitions of a sample space S. But this A is not the part of the partition. Okay. But it is an event of a sample space S. Got it? So then we can tell that P of EI bar A, P of EI bar A, that is nothing but selecting the bag from where? Sorry, selecting the bag 1 depending on what? Depending on drawing the white ball. This is what I considered before, right? So this can be written as what here? P of EI into P of A bar EI all divided by summation j from 1 to n P of EJ into P of A bar EJ. So if you remember that expression, if you have written down somewhere, please watch that. In the denominator I got sum, that is addition there. The same thing here I am generalizing, because I have got 1 to n events. There are many events. I can't keep on writing it. Instead of that I have generalized here. Okay. So I use the summation here. Now we shall start proving it, students. So now to prove this, we need to see what are the given. So what is given here? It is given that these events E1, E2, E3 and so on up to En are the partitions. So it means if these comes under partitions, what does it mean? It follows those 3 rules what we considered before. Is that right? What are those 3 rules? The first rule was, so let us start the proof. Given that E1, E2 and so on up to En are n partitions of S. Right? Therefore we can tell that first condition, what is that? E1, E2, E1 union E2 union and so on up to En equals to what? S. The second thing, EI intersection EJ equals to what? Empty for I not equal to J and I comma J equals 1, 2 and so on up to N. And the third one is P of EI should be greater than 0 for all I. Is that right? So now using these prerequisites, let us start proving. So students, this was not only the given thing. Was this statement only the given thing? No. There was there was one other thing, that is nothing but A is any event of a sample spaces. It means we need to use it, right? So now here also given that A is an event of S, right? It means what? A is a subset of S. If A is a subset of S, then we can write that A equals to A intersection S. Is that right? I think you have seen this while doing the sets problem, right students? So A equals to A intersection S. Now here if we see S, I can't do much about A, but I can do something about S here. Why? Because already we know that S is nothing but here what? Union of all these events. Is that right? So now here I can write A intersection E1 union E2 union and so on up to union En. So now if you observe here you have got union and outside you have got intersection, right? If all the operations were same, then we could have gone with this associative property. But what is happening here? Here the operation is different and here the operation is different. So what we need to do now? We need to go with, yes students, you are right, we need to go with distributive property, right? So if we use the distributive property, then we get that A intersection E1, next union A intersection E2, union, and so on up to A intersection En, right? Now we are almost close to the expression or equation what we require. Okay, so now students, we have got this. Now can I apply the probability directly here? No students, never do it, because we have just used the first what rule. Now we need to come across the second rule. What is the second rule, students? Pairwise mutually exclusive events. So this plays a very important rule here. What is pairwise mutually exclusive events? If I consider any two events and we need to check whether there are common elements, and if there are no common elements, then their intersection will be what? Empty, right? And definitely the probability will be what, students? 0, right? So here EI intersection EJ is equal to empty, and rest of the things I have mentioned here, it's enough. Now what is A intersection EI? A intersection EI is a subset of EI, and A intersection EJ is a subset of EJ. Okay, so definitely E1 and E2, if I consider I to be 1 and J to be 2, because I not equal to J here, okay, so here the intersection E1 and intersection E2 will be what? Empty, right? So here also, students, if I consider some subset of E1, then A intersection E1 will be what? It is nothing but the common elements shared with EI, that is E1, and A intersection EJ means what? This is nothing but the common elements shared with E2, right? So here already I have told that E1 and E2 does not have any common elements. Definitely, students, this and this will also not have any common elements. Therefore, I can clearly tell that their probability is equal to 0, since, what is the reason? Since here A intersection EI, right, then intersection A intersection EJ is always empty. Therefore, now if we take the probability, it will be what? 0. So now if we come across the addition theorem of probability, what is happening here? For every two events, the intersection will be what? 0. So we know that P of A union B was what, students? P of A plus P of B minus P of A intersection B. Now here this is empty, therefore probability of this is what? 0. If we consider this whole thing as this A, if we consider this whole thing as B, then probability of whole thing is what? Yes, you already tried. This will go to what? 0 every time. So if this goes to 0 every time, what we are left out with? We are left out with only these two things. Got it? So based on addition theorem of probability, now we can express the above, that is this one, that is P of A equals P of A intersection E1 plus P of A intersection E2 plus and so on up to P of A intersection En. Okay, so now you saw here intersection, right? So when it comes to intersection, immediately we need to think about the multiplication theorem of probability. So assuming that you know multiplication theorem of probability, what does it states? Yes, students, it states like this, that is probability of P of A intersection EI equals P of EI into P of A bar EI. Got it? So this is the multiplication theorem of probability, right? So using this, what I can do here? Now this further can be written as P of A equals here, instead of EI, what I can write here? P of E1, right, into P of A bar E1 plus P of E2 into P of A bar E2, right, and so on up to where? Up to P of En into P of A bar En. So now we got the total probability of this event. What is this total probability? Yes, we know that we are selecting the white ball, right? So total probability means what? How many opportunities we have got to select the balls? So here, what are the opportunities I have? I can go to the bag one. Yes, I have gone to the bag one. Then what I do there? I select the white ball. Next, what is the opportunity I have got? I can go to bag 2. I can select what? White ball from there. So if I keep on moving like this, I have got n bags where I can select white ball. Okay, so selecting white ball is totally dependent on what? It is dependent on the bags which I reach, because each bags will have different white balls. Remember that. Got it? So now we have got this, right? Now what I need to do, I need to prove the main expression. For that we need conditional probability. So what is conditional probability? So by conditional probability, so what we are finding, what is our question is now, what is the probability of selecting the bag 1, right? If we know that the white ball is drawn, it means, let us consider in general that bag E1, instead of bag 1 it can be bag 2, it can be bag 3, it can be any one of the bag of n, right? Any bag of n. So here we can write it as in general P of EI bar A. This is what I need to find. Selecting a particular bag, say EI, this I ranges from where? 1 to n. Given that what? It is a white ball, right? So what is this equal to? This is by conditional probability. I can write this as P of EI intersection A divided by P of A, because we know that if A and B are any two elements or events, then P of A bar B equals to what? P of A intersection B divided by P of B. This is what the definition we have. Based on that definition, I am writing this. So already we know what is P of A. What is this P of A? How can I generalize this? J from 1 to n, because there is sum here. Therefore, I am taking summation, right? So this can be written as what? P of Ej into P of A bar Ej. Is that right? Now, let us use this P of A in the above. Therefore, here we get summation j from 1 to n P of Ej into P of A bar Ej. Right? And then in the numerator, what we can do? Again, use the multiplication theorem. What is that? So it is nothing but P of EI into P of A bar EI. Right? So which is nothing but here, which is equal to EI bar A, where this I ranges from what? 1, 2, 3 and so on up to n. So this is the required equation, right? And first, in the example which I took, you can see the similar equation of this, right? So students, let us meet in the next class and discuss some problems on the Bayes theorem. Yeah, let us end the class now, students. Thank you.